Okay, so and now we're going to have a paper on conversational recommendation. Naomi Maro is going to talk about self-supervised bot play. Sounds like fun. And we will be hearing about transcript free conversational recommendation.
Awesome. Thanks for the introduction. Sorry, I was just muted there. But I'm Shuyang Li, and I'll be presenting about self-supervised bot play for transcript-free conversational recommendation with rationales. So this work was done at UCSD with Bodhisattwa, Prasad, Majumder, and our advisor, Julian McAuley. So I'd like to start by going over the idea of conversational recommendation. So we have an example here on this slide where we have a user on the right here who is a seeker who engages with an expert, here represented by the bot on the left, over multiple turns of conversation. And the goal is to give a personalized recommendation that satisfies the user's preferences. And here you'll notice that if we want the user to trust the recommendations that we give, we need to do that by explaining our rationales as to why we suggest certain things. And as the user, interacts over multiple turns, the information that we present them helps them to make decisions. Now, people have, tried to build conversational recommender systems like this in a few different ways, right? With some great work, especially in the past couple of years in the space. So one approach is via question answering, kind of like an interactive search, where you ask a user a series of yes/no questions and then try to restrict your search space that way. What this also ends up doing, though, is restricting the user's ability to have sort of meaningful interaction with the agent beyond Boolean, yes/no answers. On the other side of the spectrum, there are conversational chatbots, which allow for arbitrary user utterances. And this also comes at a different cost, which is that they require a lot of dialogue transcripts to train, which can be extremely expensive to source or construct these kinds of data sets. And that's especially true in domains with specialized knowledge or with specific user preferences that maybe your workforce is not able to reconstruct perfectly. And this could include common domains too, like electronics, books, alcohol, and music, things like that. So bridging that space between highly limited and flexible feedback are conversational critiquing approaches, which have become popular in the past couple of years. And that lets the user give feedback about a range of predefined but relatively large series, 50 to 70 subjective aspects about an item, much like in the previous conversational example that we showed. And that sounds great on paper, but previous state-of-the-art approaches for critiquing have shown that there's really a very large space for improvement in practice when the user needs to engage with the agent over multiple terms. So how do we take a stab at that, right? How do we train an agent to perform multi-turn recommendation with rationales without having access to large amounts of expensive constructed data? Well, recall here that what we want to do is to mimic a relatively common conversational modality between humans, right? So in this example here, let's say you're visiting a friend in, like here in New York, right? And you want to find a place to eat dinner, maybe. So in this case, your friend who you're visiting plays the role of expert, right? They're basically trying to guess what restaurant you might like the most. So maybe they suggest, hey, you might like, we might want to go to 11 Madison Park. It's fancy, it's expensive, it's vegetarian now, but maybe you're not feeling it that day, right? Maybe you're tired and you don't want to go to a fancy restaurant. So your friend will then need, in this fourth step here, to revise their understanding of your current preferences and then make another suggestion. And this, presumably repeats until you finally settle on a place to eat, or God forbid, you don't find any place at all. So that second half we just talked about, right, is this challenge for existing systems. Because we don't have ground truth user feedback, right? How do we explicitly train our expert to take that feedback into account then? To put it another way, right? You can't go back into your training set to a training user and ask them, if I recommended you something else with this different rationale, why would you dislike that? What about the item would you dislike? So we propose a way to bypass that problem. So our solution is to use a bot play framework to simulate user critiques based off of known subjective aspects that the user has already expressed in their reviews of a target item in the training set, of course. So for example, if in their ground truth review, the user doesn't mention fanciness, right? We can infer that they don't necessarily care as much about eating at a fancy restaurant. Right? So we can pick that as a simulated critique in this case. And our system basically then learns to encode that critique into the preference space, the latent user representation space, and move our understanding of the user's current preferences. So this method ends up working really quite well, and we demonstrate its effectiveness through the usage of a relatively simple model architecture with 3 main parts. So first, you have the recommender model or recommender system here, which just selects what to recommend by ranking items. You then have a justification model or justification head that explains why a user might like that suggestion. And then finally, we have a critique encoder that encodes a user's feedback into the latent space, where we can then use it to update our latent user representation. So our method doesn't really require any super complicated models here, right? Our recommender system, as shown here, can just be 2 learned matrices for user and item embeddings. And the justification and critique heads can both be just linear layers or a 1-layer feed-forward network. So we ran our experiments on 3 real-world data sets to establish how effective our method is. So it's Beer Advocate on the left, Amazon Music in the center, and then Goodreads on the right. And here I've just listed out a couple of examples of rationales that users have given in reviews to explain their reviews in bold. Right, so beer, for example, is often described using taste words or flavors. Music can be described by emotions or lyricism, and then books by sometimes more abstract concepts like how complicated it is, or glowing descriptions or text or the way it's written. So for each of these 3 data sets, we evaluated our models in line with prior work with user simulations. So given a user and a target item that the user has reviewed, we simulate up to 10 rounds of critiquing with 3 different user models. So first, a user model that critiques the most popular rationales first. Secondly, one that randomly selects a rationale to critique. And then finally, one that simulates a more knowledgeable user or with stronger preferences that picks a rationale that differs the most in frequency between the target item and the recommended item. And we got quite good results, honestly. We compared against 4 strong state-of-the-art baselines in conversational critiquing. And then in the top 2 graphs here, we actually compare our models in orange against the strongest baseline that we used in blue, which is CEVAE. So in the top left, we show success rate, which is the likelihood that we recommend the exact target item that the user is looking for out of a couple thousand possible items by the end of the session. And then in the top right, we show the average session length for that model. So our strongest baseline has a less than 10%-ish success rate, right? If it doesn't get the answer right on the first try, oftentimes it kind of just flounders in the conversation. It doesn't really improve the quality of the recommendation. And it almost always times out at 10 turns without that much success. Now, if we look at PL-RecBot, which is the rightmost column here in orange, that uses our approach with the bot play fine-tuning and then a model of the same size as this baseline. And we can see that with the same number of parameters, our approach allows us to fine-tune models to achieve 5.5 times higher success rate than the baseline in the 40s. And our average session length also drops to a sub 8 in this case, which we can see opportunities to improve that further, but it's already a decent improvement. So that shows that our bot play approach is actually effective. Now, if you turn your attention to the middle bar here, so BPR bot, also in orange, that's our model where the recommender system is trained in a different way with matrix factorization. And also, depending on the data set, it can also be up to 10 times smaller than the baseline. But we still outperform our baseline model by 3.5 times in success rate. So that's even stronger evidence, in our view, that it's our bot play fine-tuning that is doing the heavy lifting, really, to enable multi-turn critiquing. And then the final piece of evidence for that is in the bottom left here, the table or the graph titled success rate versus DIM, where we tried setting different latent dimensionality to dictate the model size. And you can find that you can see that there's almost a linear relationship here between the model's hidden dimensionality and the success rate, which shows that our bot play framework can help models understand the nuances of navigating not only simple but also relatively more complex preference spaces. So at this point, right, we've established that our framework is simple and is effective, right? And that benefit is architecture and size agnostic. Now, but the critiquing setup that we've talked about so far assumes that the user only gives one piece of feedback per turn, and that's not necessarily realistic. In user studies, we found that users actually ended up giving up to 2 pieces on average of feedback per turn. So we then studied that in the bottom right graph, right? Success rate versus number of critiques. We basically varied the number of critiques given per turn and measured success rates. And surprisingly, our bot play method allows our models to effectively accommodate multiple simultaneous critiques or multiple simultaneous pieces of user feedback with substantial improvements for every additional critique that the user provides. And that's pretty strong evidence that our approach can be used to train conversational recommendation agents that could be useful in the real world. As far as human studies go, we also conducted a human evaluation comparing simulated dialogue traces, as well as a cold start user study using our model compared to non-bot play baselines. And in both cases, humans rated our models to be significantly more useful and adaptive than baselines, right? They thought our models and their updated suggestions more faithfully represented the feedback that users gave, which is a step in the right direction, again, of increasing user trust in conversational or interactive agents for recommendation. So to bring that all back and just briefly summarize in the last 20 seconds or so, in this talk, I first introduced a critiquing paradigm for conversational recommendation that aims to imitate a common human interaction pattern, right? A user seeks a product, an expert agent tries to recommend different things and explain why they might be suitable for the user. And then we presented an inexpensive bot play framework for training agents in that expert role and showed that they're highly successful at finding suitable items over multiple turns. And with that, thanks for your interest, and I'm open for questions.
I'd a little bit more detail about the sort of the human part of the experiment. Sort of what was it that people were doing in terms of trying to evaluate the different models.
Sorry, I think I couldn't hear the first half of that question, but I heard it was about more detail about the human experiments that we conducted.
Yeah, right? Exactly. What was it that you did exactly to get that information?
Cool. Yeah. So one half of the human evaluations were comparative studies. So we actually took some of the simulated traces that we did in our offline evaluation and then presented those to human raters and asked them a series of comparative questions. So, of these 2 conversations, blinded to the model, of course, in random order, which experts seemed to be more knowledgeable about the products, which experts seemed to take user feedback into account, like did that reflect the user feedback more accurately, and which conversations seemed more successful to you. And then in the cold start user study, what we did is we mocked up an interface. Well, I guess we actually built an interface in that case for book recommendation, where the user was presented with an item and then given a list of, I believe it was up to 5 or 7, no, 5 of the top recommended rationales for why the item was recommended to them. And then the user was able to select an arbitrary number of those to provide negative feedback and say, I didn't like this item because of that. And then at each turn, we then refresh that, given the feedback to the model, and then allow the user both at every turn to give feedback about, oh, the model, did it take into account my feedback from the previous turn? Are these rationales useful for me? Do these rationales accurately reflect my understanding of the product? And then finally, they can mark the conversation as succeeded if the target item or market item that they liked was found. And then they could, at the very end, say, was it successful, and give sort of free-form feedback about that.
Okay, great, thank you. I'm afraid that's all the time we have, but be sure to check back on the paper page because there's a number of questions here to follow up. All right, let's thank the speaker again.